All right, welcome to Lab 8. The goal of this lab is to take a 4-bit binary number and change it into sign magnitude, ones complements, and twos complements. So for the first task that we have, we're going to kind of focus on doing the ones and twos complement. And the way we do this is that we are going to start off with first off understanding what we would get for a not or for inverting our zeros into ones when we do our ones complement. So when we have our enabler off down here at the bottom, we see that we have our value 0, 0, 0, 0, and that turns into 1, 1, 1, 1, which is the ones complement of 0, 0, 0, 0. So when we change any numbers, we see that the numbers get flipped from 1 to 0. And the way we accomplish that is that we're passing these values into the NOT gate, which inverts it, and then we put it back into our adder. So any value that we pass through here, with the enabler off, we can do a ones complement. So let's go to the twos complement form when we turn the enabler on, and then we'll just do this right here, which the twos complement is basically we read it from right to left, and we go until we find a 1, and then every digit after that we either switch it from 0 or 1 depending on what the value is. So we have value 2 right here, so then we get the output of 1, 1, 1, 0, which is a 2's complements form, and then let's say, for example, 0, 1, 1, 0 should be 0, 1, 0, 1, which is correct. Then we can do this right here, and then 0, 1, 1, 0. So that all works fine and dandy. So then we move on to our next part, which is task B, which is pretty simple. It's just doing the sign magnitude. So only the really thing that we need to worry about is just changing our most significant bit into a 1 when we change our sign magnitude. So we see we have our conceptual circuit here. The only gate that we need is the exclusive OR gate. And whenever we have an exclusive OR gate, it'll pass the value of 0, 1 and 1, 0 through, but it will not pass true if both inputs are either 1 or 0. So with that, we can pass it onto our chip. It's pretty simple design. All we got to do is just connect our most significant bit and our enabler into our exclusive OR gate, and then just pass that value through to our most significant bit. So we got here 1, and then that stays the same, and that's off. Do that, and then all the other numbers will stay the same because they don't change. It's just the most significant bit that changes. And then we add everything together. So it looks kind of complicated here, but basically what I did was I started with our ones and twos complements and just kind of put everything together through there. Earlier in the lab today, we were having issues with trying to get our most significant bit to work, and I found what our issue was. We had our most significant bit going into our A1 value, I believe. I don't really remember. I just remember seeing that our least significant bit was actually the value being passed into our XOR value, which made our least significant bit change its value. So it was pretty simple fix. Looking at it conceptually over here with the chips, all you had to do was just switch the least significant bit into going into the right NOT gate, and then the most significant bit going into the right NOT gate, and also going into our exclusive OR gate. So that was the issue that we were running into. That's why we couldn't get our sign magnitude to work, but we got everything working now, so that's a good thing. So then, added the sign magnitude and just added our data data selector, or also our multiplexer, and just hooked up everything to where it belonged. So now we can do 2. Let me see, we got our 2 binary value of 2 over here. So when it's 0, 1, when we do sign magnitude, we get 1, 0, 1, 0. And then when we do ones complement, we get 1, 1, 0, 1. And then when we have both of them, which is our 2's complement, we get 1, 1, 1, 0. And that works for all values. So let's do 5. Just have some fun, I guess. So we have 5. So we got 5 over here. We do our sign magnitude, we get 1, 1, 0, 1. And we do our ones complement, we get 1, 0, 1, 0. And then when we do both of them, we get our 2's complement, which is 1, 0, 1, 0. And again, reading it from over here from our input, this is our most right one, and then switching the values of 1, 0, 1 after that. And that's what we have over here. So yeah, so that's lab 8. Just doing a little minor fix, probably one of the most simplest fixes, probably something that we couldn't see originally, but we were able to get it done through here.